Hello and welcome to all friends. Today we will see the unit number 4, passive microwave components, in which the today's topic is the analysis of magic tea and applications. So in earlier lecture we already saw the different properties, the construction details and working of the magic tea, and based on that we form the scattering matrix. And according to the scattering matrix, now we will see the different properties of magic tea and some important cases of the magic tea, and we will validate the properties of the magic tea. So before going to that, we will see what is the exactly the magic tea scattering matrix is available. And here if you see the magic tea scattering matrix, then the B1, B2, B3, B4 are the reflected voltage, whereas the A1, A2, A3, A4 are the incident voltage available. And the scattering matrix is available over there. Based on that, we will get it the equation B1 is equal to 1 by root 2 in a bracket A3 plus A4 bracket complete. B2 is equal to 1 by root 2 in a bracket A3 minus A4 bracket complete. B3 is equal to 1 by root 2 in a bracket A1 plus A2 bracket complete. B4 is equal to 1 by root 2 in a bracket A1 minus A2. So these are the important equation, and on the basis of that we will go for the different cases. Now case number 1 is that where we are applying the power to the port number 3, and the port number 1, 2 and 4 there is no power is applied. Now if you put it this condition in equations, 18 number equation like B1, B2, B3, B4, then we get it the net result of the B1 is equal to A3 by root 2, B2 is equal to A3 by root 2, whereas B3 and B4 is equal to 0. So this shows that if we are applying the power to the port 3 as an input power, then we will get it the power at the port 1 and the port 2 equal in magnitude and with the same phases. So this is the kind of a property of a H-plane T. Similarly, case number 2, if we are applying the power to the port number 4, at that time the port number 1, 2, 3 is equal to 0, then we will get it the equation B1 is equal to A4 by root 2, B2 is equal to minus A4 by root 2, whereas B3 and B4 is equal to 0. So whenever we are applying the power to port number 4, we will get it the power at port number 1 and port number 2 equal in magnitude but opposite in phases. So this is the kind of a property of E-plane T. Now similarly, the case number 3 we will see where the A1 is not equal to 0, so we are applying the power to the port number 1, whereas the A2, A3 and A4 is equal to 0. So that time we will get it the equations B1 is equal to 0, B2 is equal to 0, B3 is equal to A1 by root 2, B4 is equal to A1 by root 2. So these all are the cases we get it over there. Whenever we are applying the power to the port number 1, we will get it the power to the B3 as well as the B4. So that is when the power is fed into the port number 1, nothing come out to the port number 2, even though they are collinear ports like a magic. So here we are applying the power to the port number 1, your power will not be applied to the port number 2. So it's a kind of a magic we get it over there. Hence port 1 and port 2 are called as isolated ports. Similarly, an input at port 2 cannot comes out at the port 1. Similarly, E and H ports are isolated ports. So this is the case number 3 we get it. Now the case number 4, in that A3 is equal to A4, like we are applying the same amount of power at port 3 and port 4. That time the A1 and A2 is equal to 0. Then we get it B1 is equal to twice of A3 by root 2, whereas B2, B3, B4 is equal to 0. So this is nothing but the additive property equal input at port 3 and port 4 results in an output at the port number 1 in phase and equal in the amplitude. So this is the case number 4, whereas the case number 5, A1 is equal to A2, like we are applying the power to the port 1 and port 2 similar manner, whereas A3 and A4 is equal to 0. Then we get it a B1 and B2 and B4 is equal to 0, whereas we get it a power at B3 is equal to twice of A1 upon root 2. This is equal inputs at port 1 and port 2 results in an output at the port 3, that is the additive property, and no output at the port 1, 2 and the 4. This is the similar case of the case number 4. So these are the all about the properties of important properties of the magic T, and from these equations we validate all the properties of the magic T. Now we will see the applications of the magic T. Now a magic T has several applications, and few of them here we will discuss. So the first application is the measurement of impedance, where a magic T has been used in the form of the bridge as shown in the figure. Microwave source is connected at the arm number 3 and the null detector is connected to the arm number 4. The unknown impedance is connected to the arm number 2, that is port 2, and the standard variable resistor impedance is connected to the port number 1. Now if using the properties of the magic T, the power from the microwave source A3, which is moving one, gets divided equally between the port number 1 as well as the port number 2. Which are the unknown impedances and the standard variable impedances available. These impedances are not equal, and that's why the imperfection of matching takes place, and quite obvious that the reflection will be coming back over there. So here we will see that the reflection coming on from the port number 1 from the standard variable known impedance, that is the 1 by root 2 A3 rho 1. Similarly, from the unknown impedances, we will get it the reflection 1 by root 2 A3 rho 2, and this will be entered the magic T junction from arm 1 and arm 2 to the arm number 4, that is the null detector, and this null detector output can be calculated as equal to 1 by root 2 in a bracket 1 by root 2 A3 rho 1 bracket complete minus 1 by root 2 in a bracket 1 by root 2 A3 rho 2 bracket complete is equal to 1 by 2 A3 in a bracket rho 1 minus rho 2. That is 1 by 2 A3 in a bracket rho 1 minus rho 2 is equal to 0. Therefore, rho 1 minus rho 2 is equal to 0. So we can say that the reflection coefficient rho 1 is equal to rho 2. So this shows that the Z1 minus ZZ upon Z1 plus ZZ, that is related with the reflection coefficient rho 1, and Z2 minus ZZ upon Z2 plus ZZ, this is related to the reflection coefficient rho 2. So here for the perfect matching, and we will get it a 0 reading here. Z1 is equal to Z2, that is R1 plus JX1 is equal to R2 plus JX2. So we equalize the real part and the complex part. So here we get it R1 is equal to R2 and X1 is equal to X2. Definitely the complex conjugate part should be available over there. And based on that, we can say that the unknown impedance can be measured by adjusting the standard variable impedance till the bridge is balanced and both impedances become equal. So this is the first application, we will observe the measurement of the impedance. Then the second application is that the magic T as a mixer. So here the transmitter and receiver are connected to the port number here magic T as a mixer. In that we can see that magic T can also be used in a microwave receiver as a mixer, where the signal and the local oscillator are fed into the E and H arm. Half of the local oscillator power, half of the local oscillator power of the and half of the received power half of the received power from the antenna goes to the mixer, where they are mixed to generate the intermediate frequency. So you can see from the port number 3, the power will be divided equal manner here, and the signal received from the antenna, we will observe one that is called as F in here. This will be equal manner divided over there, and here since at the mixer point here, you can see that it is nothing but the F in minus F0, which is called as the intermediate frequency. So here the difference of component takes place because of this is the port 4 as a E arm, and that's why the out of phase component we get it here, and that's why the subtraction will be available F in minus F0, and the result is that we generate the intermediate frequency, that is the output of the mixer. So this is the particular application we get it over there, Magic T as a mixer. Whereas in case of the Magic T as a duplexer, the transmitter and receiver are connected in a port 2 and a port 1 respectively. Antenna in the E arm at port 4 and port 3 of a Magic T is terminated in a matched load, which is shown in a figure. During the transmission, half of the power reaches to the antenna, from where it radiates into the spaces. Other half reaches the match load, where it is absorbed without the reflection. No transmitted power reaches the receiver, since the port 1 and 2 are isolated ports in a Magic T. During the reception, half of the received power goes to the receiver, and other half of the power to the transmitter are isolated during the reception as well as during the transmission. So this is the application of the Magic T as a duplexer. Thank you very much.